Hello, in this video we're going to talk about isomerism. And so I'll start this off with a problem, and I encourage you to read the problem, pause the video, give it a shot, and then I'll come back and we'll talk about the answer. Okay, so we start out drawing the Lewis structure, and so this molecule has 36 electrons. And alright, let's lay it out like this. I'm going to decide to put the two fluorines on the same side. We'll get back to that in a few minutes. Alright, put the electrons around. The electronic geometry, well, since there are 6 electron groups around the central atom, the 4 atoms and the 2 lone pairs, that makes the electronic geometry octahedral. But since 2 of these are lone pairs, the molecular geometry, which you name just from the atoms, is going to be square planar. Now the bond angles on something that's square planar are 90 degrees, because the lone pairs push equally on opposite sides of the central atom, and so the peripheral atoms on the outside are all still 90 degrees from each other. Okay, well, why did I draw it this way? Why did I put the 2 fluorines on the top? Or, as we were drawing it, on the top. Why couldn't I have done it this way and, I don't know, put the 2 fluorines across from each other? That would mean the chlorines would go here, and then we drop our electrons around, and we have a different molecule. Or maybe it's the same molecule. Well, let's talk about that. First, before we do that, the molecule on the right, the electronic geometry is still octahedral. It's still a square planar molecular geometry. The bond angles are still 90 degrees. Those things are all the same. But now when we get to polarity, well, there becomes a difference. So on the left one, the xenon to fluorine bond is more polar. It has a higher electronegativity difference across that bond. And so I drew it with longer arrows to represent that, because fluorine is more electronegative than chlorine. So the xenon-chlorine bond is less polar. Now, these don't add up equally. We're left with a net dipole moment that points up in the direction of the fluorines. And this molecule is polar. Well, on the other side, well, the 2 xenon-fluorine bonds are now across from each other, 180 degrees away from each other. And so those 2 will cancel. The 2 chlorine bonds will cancel. And so this molecule is nonpolar. So what gives here? Turns out that this molecule you can make in 2 different forms, one of which is polar, one of which is nonpolar. These 2 forms are called isomers of each other, geometric isomers, and we give them names. We call the one on the left cis, because that's the Latin root word for the same side. The 2 fluorines are on the same side of the molecule. The 2 chlorines are on the same side of the molecule also. The one on the right we call trans, because the 2 fluorines are across the molecule. You transit, you go trans across, take a transatlantic flight, that kind of thing. And the chlorines are also across the molecule. Okay, so we have 2 different molecules, cis and trans, and here's a book drawing of the same thing. Okay, so this leads us to isomerism. It's the idea that you can have a compound that has the same formula, so a molecule with the same formula and different structures. Those different structures will often have very different properties. That's why it's important that we talk about this. And we broadly delineate this into 2 categories: structural isomers, where you have the same atoms but they're just bound differently to each other in different places, if you will. And then we have stereoisomers, which have the same bonds but different spatial arrangements. And you can divide this into geometric isomers, which is the kind we just saw, and optical isomers, which we'll also talk about. So structural isomers, again, have the same chemical formula but different connectivities. So you can have 2 different molecules. One is called propanol, where the oxygen is on the right side of the molecule. One is called isopropanol, which you buy as rubbing alcohol, where the oxygen is kind of in the center of the molecule. These have the same chemical formula, but they have different connectivities, they have different properties, a different boiling point, things like that. And so we have to treat these molecules differently. They are isomers of each other. So these are structural isomers. And that's, I guess, pretty straightforward. Whether it's connected one way or the other, it's pretty obvious that it's different. how to name these things is beyond the scope of this class. When you get to organic chemistry, you'll have a way to name them. But for us at the moment, we're not going to worry about naming structural isomers. We will, however, name geometrical isomers, so let's talk about that. Geometrical isomers are in the stereoisomers category, the other side of that flowchart, where there's the same chemical formula and bonds, but yet different spatial arrangements. So geometric isomers, there's different geometrical arrangements around the center. Our opening example showed us this. This new molecule here, sulfur with 4 fluorines and 2 chlorines, if you've got one where the chlorines are next to each other, so this is 90 degrees, then that's one molecule. If you have another one where the chlorines are across from each other, well, that's 180 degrees, and that's a different molecule. Again, we call the one on the left cis because it's on the same side, and the one on the right we'll call trans because they're on opposite sides. So you say the cis isomer or the trans isomer. Geometrical isomers are often called cis-trans isomers from these two different names. So you can say cis-trans isomerism if you want. Okay, another example, cisplatin, which is an anti-cancer drug, has the 2 chlorines on the same side of the molecule, cis, right? They're on the same side over here. Whereas transplatin has the chlorines across, has no therapeutic effect, it's just toxic. So the geometry here really does matter, especially when you're making drugs or things that need to go to some biological receptor, which is picky about shape. And the shape and polarity of these 2 molecules are going to be very different. They're going to behave very differently. Okay, so that's geometrical isomers. The next thing we talk about are optical isomers. Now, these are a little harder to see. Fortunately, your hands are optical isomers of each other. If you take one hand and hold it up to a mirror, you see the other hand. So here there's this person's left hand, and then up in the mirror is their right hand. Well, they're mirror images of each other. Okay. But your 2 hands are not superimposable on each other. In other words, you can't take a left-handed glove and put it on a right hand very well, right? Because your hands are very different. So they're mirror images that are non-superimposable. You can't put your right hand over your left hand and have it match up. And these are called optical isomers, if you have a molecule that does the same thing. Another word for optical isomers is chiral. This is a chiral molecule in that it displays optical isomerism, or it could display optical isomerism. And so a couple examples here. Tetrahedral compounds where there's 4 unique groups bound to the central atom. And so here you have a mirror plane in the middle, and then you're reflecting these atoms over the mirror plane. So the carbon's still in the middle, and then the bromine, well, it's closest to the mirror on the left, so it's going to be closest to the mirror on the right. The fluorine, okay, it's on the mirror on the left, down on the right here, kind of in the lower spot. The iodine's farthest from the mirror on both sides, and the hydrogen still points up. So if you do this, you now have a different molecule. You cannot rotate the molecule on the right in any way to make it line up with the molecule on the left. And please remind me if I don't do it already, this is easiest to see with models in class. So we'll have to show that. Okay, so these are optical isomers of each other. We have another example that we do in the end of the 2nd semester of general chemistry, which is these transition metal complexes, which will adopt either tetrahedral or octahedral geometry. And if you have these ligands, they're called, that bridge between 2 of the nitrogens attached to this iron, well, you can put these ligands in different ways that you'll have optical isomers. If you reflect it over a mirror plane, this one is the same as that one, for example, then you'll get a new molecule that you cannot rotate to line up with the first one. And that's optical isomers. So let's talk about the words a little bit. So optical isomers, you use that word to refer to a pair. Just like you say, they're a couple. You're talking about 2 people at the same time. So optical isomers, you generally say that if it's talking about 2 molecules, they're optical isomers. You can say that one of those can display optical isomerism, just like one person could display coupleism, if they so choose. And then a chiral molecule refers to an individual molecule. This molecule is chiral, meaning that it has the ability to have optical isomers. Not all molecules can, right? There's many molecules that if you reflect them through a mirror plane, then you just get the same molecule again and nothing's different. And those are not chiral, or they cannot form optical isomers. Okay, so most biologically significant molecules are chiral. I hinted at this earlier that many of these molecules are either getting built, in the case here there's amino acids and they get built into a protein through some molecular machinery that does that, or they're drug molecules, for example, and they have some place in the body where they're trying to go, kind of like a lock and a key in a way, right? Like they're going into one spot and they need to fit. And if they're the wrong shape, even if it's the right atoms bound in the right order, they're not going to fit. So here we have examples. We have D and L-alanine. And this is not something I need you to know in general chemistry, but this is something you do learn in organic, that D and L are just markers. This comes from the way that these molecules rotate a certain form of light. Dextrorotatory and levorotatory is what it stands for. But you don't need to know that now. Just realize that they're identifiers of one-handedness and the other-handedness. So one of these is like a left hand, one is like a right hand. And it turns out that only the L isomers of amino acids work in biology on this planet, pretty much. However, that's not exclusively true, right? Bacteria have some D amino acids. And hey, this molecule penicillin, it works by blocking the proteins that work with D amino acids. So that means they don't hurt humans, which are all using L amino acids, but they'll hurt bacteria. So just one of many examples of how isomerism really matters in biology. Okay, so we'll end with some practice problems. And so I encourage you to pause the video, try these, and then turn the video back on, and then we'll go through the answers. Okay, for the first one, I'm going to start by drawing the chlorines across from the cobalt, and then put the other atoms around. And that's one of my isomers. Then now I'm going to take the other option, and I'm going to draw the chlorines next to each other somehow. And honestly, you can put the chlorine in any one of the spots that was previously occupied by a bromine. I just picked the one on the right because I liked it. And then put the other atoms around. Okay, so your isomer on the right is cis because your two chlorines are next to each other. And the isomer on the left is the trans isomer of this molecule because the chlorines are across from each other. When looking at these, I find it easiest to pick out the unique atoms and decide whether they're next to each other or across from each other. I think that works best. Okay, for the next one, it says there's a carbon-carbon double bond in the middle, and then a hydrogen and a bromine on each side. Okay, so I did it this way, where I put the hydrogens across from each other, and the bromines are across from each other. And so then this makes this trans across this double bond. And then the other option is to put the two hydrogens on the same side of the bond and the bromines on the same side of the bond, and that makes this one on the right cis. Now this is only possible because the double bond doesn't rotate, and we'll talk about that later, because that, if this double bond rotated and you could spin the hydrogens and the bromines around, then this would be a moot point. But double bonds don't rotate, and so this works, and we'll talk about that part of it later. All right, the last one, draw the optical isomers here. So easiest way to do this is to make your mirror plane, and then copy the carbon atom over, and now put the atoms on. Okay, so I'm going to put the one closest to the mirror on the top, similarly closest to the mirror on the top, on both sides. I wrote it this way with the carbon connecting to the other carbon, because that's how this actually works. And then the hydrogen is on the top, but farthest from the mirror. On the bottom, the NH2 is farthest from the mirror. Again, I connected the N to the bond because it actually bonds to the nitrogen and not the hydrogens. And then on the other side, I wrote it backwards this time because it bonds to the carbon, and then the oxygens and hydrogen go out from there. And so this is on the bottom closest to the mirror. And again, I could rewrite the one on the top this way if I wanted, and that would be perfectly legitimate. Now we're getting into nuances that are more organic chemistry than general chemistry, but I figured I'd include it because it makes sense here. Okay, so now we have the two optical isomers of cysteine. And you can make these 3D if you want, because this is a tetrahedral molecule and it is three-dimensional. And if you do this, don't forget to also reflect your three-dimensionality of it. The dashed bond is closest to the mirror on the left side, so the dashed bond needs to be closest to the mirror on the right side. And what this tells us is if you, say, grabbed hold of the CH2SH group and spun the whole molecule around to line up with the other one, well, your hydrogen and your CH2SH would line up, but then your nitrogen would be going into the page, and your carboxylic acid, the COOH, would be coming out of the page. And on the left side, it's the other way around. So these are two separate molecules. They're called optical isomers of each other. Each one is called chiral. Okay, and with that, we're done with this video. So thank you very much for watching, and have a good one.